Here are our solutions for homework set number 4 for ECE 463-663, Modern Control. The first problem is find the dynamics for a cart and pendulum system. Basically try to balance a yardstick on your hand. Assume the base has a mass of 1 kilogram, the length of the beam is 1.5 meters, and the mass you're trying to balance is 3 kilograms. Well, the procedure is pretty much follow along with the lecture notes to find the mass, position of the cart, its potential energy, kinetic energy. The ball up here is positioned as x plus 1.5 sine theta, y coordinate 1.5 cosine theta, and here I'm defining x and y this way. So this is x, that's y, kind of the same way the MATLAB draws on the screen. Take the derivative, we get x dot y dot. Potential energy is mgy. Kinetic energy is 1/2 mv squared. Substituting x dot squared and y dot squared, or x2, y2. Multiplying it all out, cosine squared plus sine squared is 1. Got the cross terms. Here's the kinetic energy. The Lagrangian then is kinetic energy minus potential energy. So here's the first mass, the second mass, grouping the terms together. Here's the Lagrangian. With that, I can now find the force on the cart. That's the full derivative of the partial derivative of L with respect to x prime minus the partial derivative of L with respect to x. Partial with respect to x prime gives you this term, no x dots, there's an x dot. There's no x's, so 0. Now take the full derivative. Gives you 4 times the second derivative, chain rule. Derivative of the second term times the first, derivative of the first times the second. Derivative of cosine theta is minus sine theta, theta dot, times another theta dot. So there's one equation. The second one, starting with the Lagrangian, the torque on the beam is the full derivative of the partial with respect to theta dot minus the partial with respect to theta. Partial with respect to theta dot gives you this term and that term. Partial with respect to theta, nothing, nothing. And derivative of cosine is minus sine theta. Cosine is minus sine. Now take the full derivative. Gives you theta double prime. Derivative of the second term, x double prime. Derivative of the first term. Simplify. These terms cancel. So there's the torque. So here's your dynamics. That's the dynamics for a ball and beam system. In matrix form, this is what you simulate in MATLAB. We want to simulate the nonlinear dynamics. To come up with the linearized dynamics, linearize about 0. So cosine theta is roughly 1. Theta dot squared is roughly 0. Sine theta is roughly theta. Take the inverse, and I get this. Or in state space form, this, plugging gravity. Here's the dynamics. We're going to be using that quite a bit. That's the dynamics of the cart and pendulum for this semester. When we design full state feedback controllers, that's what we'll be using. So see this again in homework set 6 and 7 and 8 and so on. Checking if you find the eigenvalues of the A matrix. It's unstable. It falls as e to the 5.11t. Next problem. Look at the ball and beam system. If I have this system, find the dynamics. So here I've got a little torque. This beam spins up and down. Ball rolls back and forth. What are the dynamics? Well, the position of the ball is r cosine theta, r sine theta. X dot is r dot cosine theta minus r sine theta, theta dot, and y dot. Assuming a solid sphere, J is 2/5 mr squared, giving you this term. That's the rotational energy of the ball. Put them all together, I have the potential energy is the mgy. Kinetic energy is the beam rotating, the ball translating, the ball spinning. Or simplifying, when J is 2, M is 1, or M is 2. What was it? M is 2, J is 0.5. Okay, so as I was saying, since J is 1/2 of a half is a fourth. That's the kinetic energy, mass, and rotational energy. So multiplying it all out, simplifying, gives you the Lagrangian as such. Now that I have the Lagrangian, I can find the force on the ball, which is going to be 0. That's the full derivative of the partial with respect to r dot, which is, where's an r dot? Right here's an r dot, and that's about it, minus the partial with respect to r. So here's an r, and there's an r. Taking the full derivative, 1.4 r double prime, and simplifying. So there's one set of equations for the dynamics. Going back to the Lagrangian, take the partial with respect to theta. So here's your theta dot. There's the theta dot, and that's it. Now the partial with respect to theta is right here. Now take the full derivative. Full derivative of 0.5 theta dot is 0.5 theta double dot. Chain rule, 2r squared, theta double prime, 4r, r dot, theta dot, no change. So I can now put these two in matrix form. Here's the r double prime, theta double prime, Coriolis forces, gravity forces, and torque. This is the dynamics that we use to simulate the ball and beam system. If I linearize it at 1 meter, then I get these equations. Taking the inverse, I can express that in state space form. So here is the linearized dynamics. Here's your A matrix. Here's your B matrix. We'll be using that when we want to come up with our feedback controllers. Stabilize this linear system, and it should work on the nonlinear system, we hope. So keep that in mind. We'll be using it later. And as a check, the eigenvalues of this system are plus 3.2, minus 3.2, plus minus j3.2. Basically, this is really hard to stabilize by hand, but a computer can do it. So that's homework set number 4 for ECE 463.